Madras. Uh, I thank the AsiaGraphics team for inviting me to give a presentation, and I thought I will do it on the geometry side because most of the others probably is in graphics. So my title of the talk is on Voronoi diagram, and it's a very famous geometry construction used widely in different fields. But my focus will be more towards the curves and surfaces. A lot of work have been done on point sets and mesh and so on, but I'll be focusing on these curves and surfaces, and I'll presently looking at some of the challenges and some algorithms that will overcome some of these challenges. So we just talk about these details as we proceed now. So I'll just go to the full view and just looking at. Okay. Sorry, guys, seeing the full view now? Is it okay?
Yes, now it's full view. Yeah.
Okay, thank you. Yeah. So many of you are probably familiar with the Voronoi diagram. Anyway, I'll just give a brief account of it. So if you're given a set of points, okay, let us start with points because it's little easier to understand with points. So if you're given n points in the plane, so the Voronoi cell basically divides the set into what is called as a closure entity set. So for example, if you want to have a Voronoi cell of the point P2, like you have a point P2 and you can see the point P2 here, and you have seen the other points P1, P2, P3, and P4. So you can see this region. If it has the region, this is the region of what is called as a Voronoi cell. Particularly, why is this called as a Voronoi cell? Because if you take any point Q inside this cell, you will observe that P2 is the closest point than to other points like P1, P3, or P4. So we can observe that the boundaries of this particular one constitute what is called as a Voronoi cell. So if you keep on building the Voronoi cell, as you can see in the next diagram here, so if you can keep on building the Voronoi cell of each of the points, so you can see this is Voronoi cell of P2, and you can see this will be the Voronoi cell of P1, and you can see that this is the boundary of P1 and P2, and if you consider all the boundaries of the Voronoi cell, then you actually get what is called as a Voronoi diagram. So you can see these edges that you have seen are constituting what is called as the Voronoi diagram for this entire point set. So some little bit of terminology. We have seen what is called as a Voronoi cell, because in a Voronoi cell, any point Q, as I say here, will be the closest one. P1 will be the closest one. If I am in the Voronoi cell of P1, sometimes it is also called as a Voronoi region. There is some confusion will come later on when we go for higher dimensions. So we will see during that time. And you can see there is a point called B, as you can observe here. So there will be three Voronoi edges coming together at this particular Voronoi point, which is called as a Voronoi vertex. So the B point B is called as a Voronoi vertex. You can see that we also use what is called as a branch point. This alternate term for that, but probably we'll stick to using the word or the terminology Voronoi vertex. So if you consider a Voronoi diagram is constituting of Voronoi edges, and whose meeting point will be the Voronoi vertices. So for example, you have another point here, which is also a Voronoi vertex. Typically, as you may observe here, the Voronoi vertices will actually have three Voronoi edges meeting together. It is not always true, but in what is called as a general position assumption, you will see that three Voronoi edges will be coming at meeting at a Voronoi vertex. But we will see that this assumption can be relaxed later on. So here is another example that you can see that we have a Voronoi diagram for another set of points. As you can see, this is a Voronoi cell of the interior point that you can observe, and this is the Voronoi cell of the other points. So you can see these are all the Voronoi edges, and this will be like a Voronoi vertex. So here is another example, but these all, as you can observe that these are all for a point set. I'll just illustrate briefly. If you take 2 points, what will happen? So if you take 2 points in the plane, you can observe that there will be a perpendicular bisector between the 2 points, and this perpendicular bisector actually becomes a Voronoi diagram, because you can see that it divides the plane into 2 halves. So any point that you take here, you can see P1 is always the closest, so this will become the Voronoi cell of P1. And any point that you take here, for example R, you can say that this will be the Voronoi cell of P2, because any point R will always be closest to P2 than to P1. But in the boundary in the Warner diagram, as you can see, they will be equidistant from both points P1 and P2. And in this particular case, you can easily observe that the bisector or the perpendicular bisector is the one that is dividing the 2 points. And you can observe that this is the Warner diagram actually for these 2 points. So if you extend this to further, you can see that if you take 3 points, you can observe that the Voronoi diagram will be consisting of the perpendicular bisectors from different pairs. So you can see that this is one of the component of Voronoi diagram, which is the Voronoi edge, and this comes from the bisectors P1 and P3. And similarly, you will see there is a component from bisector P1 and P2, and so there will be another one from P2, P3. So you can observe that the Voronoi diagram basically comes from the bisectors. In this case, as we can observe for a points, we can observe it is the perpendicular bisector that plays a role. As we go, we see that it gets going to get more complicated on that. So we can see that bisector of P1 and P3 becomes a Voronoi edge, and P1 and P2, and you can see P2 and P3 comes into picture. So as you can observe that this definition of Voronoi diagram is not just for points. As long as you can come up with a distant metric, you can actually do it for any of the other set like the curves or surfaces or any other set that you can think of. And it is also applicable to any dimensions as long as you can measure it. So now there is a definition which will just for completeness, I'll just define for curves because this is what we are going to see mostly, and then to some extent surfaces as well. So you can see that if you are given the curve C naught and so on up to, you can see that few curves that we have given here. So the same definition applies. The Voronoi cell will for C naught. So if you want to compute the Voronoi cell for C naught, basically that region will consist of all points that are closer to C naught than to other curves C1 and C2 and so on. So if you see the hashed region, the white color hashed region, so if you take any point on this region, you can see that that will be the Voronoi cell because the curve C naught will be the closest in that particular Voronoi cell. So if you keep on doing this for all other, so you can see observe in the red, these are the boundaries of the Voronoi cell. And if you continue for other curves, you will actually get into what is called as the Voronoi diagram, as you can see in this picture. But in the case of a curve, it can be little more complicated. So when you have a curve like this, which has a high curvature in some particular point, there will be what is called as a self-bisector. You can see this white dashed line is a self-bisector. Because you can see there are equidistant points come from the same curve. So for example, if you take a point R0 and R4, you will see that both of them come from the same curve C1. So this is what is called as a self-bisector, and we probably not discuss about self-bisector in this particular talk. Of course, you can always split the curve at these high curvature points and then make it into two different curves, and hence we can make this self-bisector also vanish. But it will be for two different curves then. So typically we are looking at the disjoint curves, but later on we will see that in some instances we can also negotiate intersecting curves and other degeneracies that come in the geometry computation. So here is the example for Voronoi diagram of set of curves. So these are all planar curves anyway. So there are lots of applications of the Voronoi diagram. I'm just mentioning few titles here without citing the papers. I can just go back and look at it or get back to me. So there are lots of, particularly there is a lot of focus on finite element mesh generation from the Voronoi diagram. And this is another work which is very interesting, where it helps in suppressing some of the geometric features. And of late, we can see that there are works like that are applied for 3D printing and path planning. And of course, recent works have done for 3D on hexahedral mesh generation and so on. There are a lot of applications of Voronoi, so I'm not touching them in great detail on that. So as we understood by now, like the bisector becomes a crucial one for Voronoi diagram. So let us look at some simple cases of bisectors. Okay, so maybe I'll just take a fresh thing and draw. For example, as we have understood now, between 2 points, we know that a perpendicular bisector plays a role. Suppose if I'm little bit increasing that right from points, let's say if I give 2 lines, what will be the one? Then the angular bisector will place basically the bisector between the 2 lines. So if you keep on going for other sets, for example, if you take a point and a circular arc, then the bisector has been shown to be an ellipse between them if it is inside. So we can, if it is outside, for example, for a point, and a circular arc on the other side, we can see that this will end up in what is called as a hyperbola. So this will be a hyperbola. So for some of the simpler cases, there are some closed form solutions like we have seen ellipse or angular bisector or a perpendicular bisector and so on. But we will see shortly that it can become more complicated than just a hyperbola or an ellipse. Even then, actually, it is quite complicated. So you can see that bisector between two circles. Actually, you can see now they are slowly moving into curves away from point sets as such. And this is actually, you can see that the bisector it becomes hyperbola of two sheets in general. So we have to work on a little bit of a more complicated one. And you can observe that the Voronoi diagram on the right side here, you can see that only a small portion of the wedge becomes a Voronoi edge. So you can see that the entire bisector, you have to remove these segments, retain this segment, and even then there will be only small portion that will play here. We will see how to get there. So just to indicate the complexity of bisector alone at this point. So you can observe that the bisector can become more and more complex. If you take the case of two ellipses, you can see that the bisector is indeed the shape, at least it's quite complex. So this is bringing in few challenges for us now. um, Okay, before we actually go into that, we are showing some examples on the point curve bisector. So we see points, we saw circular arcs, points between circular arcs, we saw between circles, and then we saw between ellipses. So we slowly move on to general curves. For example, you can represent a curve in a Bezier form. So if you just take any a point, for example, a point here and a curve, as you can see in this picture, you can see this is the untrimmed bisector. So eventually you can see the trimmed bisector will be a very small portion, and a lot of studies have been done, particularly by Faruqi, mathematician, and his students. And you can see that in this particular case of point and a rational curve, the bisector has been shown to be rational. Okay, so these are on the theoretical front, which we may not see too much at this point of time, but just to give a feel for the complexity of the bisector. So you can see as you increase the complexity of the shape, if you go for higher order curves, as you can see that we have two higher order curves, you can see the bisector shape is quite complex. I will do a demonstration shortly on that, how do we get there. So if you take two oval shaped curves like C0 and C1, you can see that bisector has grown in complexity. It has several components. We can see it as several components at least, though the definition of bisector is same as a single guy. But if we do some kind of juggling of that, we can split into different components, which will come back into detail later on that. So now we can observe that whenever you want to compute a Voronoi diagram, we are supposed to compute the bisector. That is a thinking process at this point of time. So we can see these bisectors are becoming complex. If it is a hyperbola or an ellipse, we know how to represent, right? We have a closed form solution, we know how to represent. But how do you represent a bisector like this? Okay, how do you represent a bisector like this? So it is not exactly in a closed form solution as we see it for other cases. So definitely it is getting more complicated on that. So the first question is that, okay, how do you represent a bisector if it's going to be complex in the case of curves? So also we can see that given a 2 degree m degree curves, we will see that the bisector degree is of 4m minus 2, which itself is pretty high. So if you take an m equal to 3, we can see that it ends up in a higher degree bisector curve. So processing that is going to become quite tough. As you can see in the next challenge, how do you go from bisector to Voronoi diagram? Because the geometry processing of bisectors are needed. One thought could be, okay, can we try intersection of bisectors? But intersection of bisector is also going to be complex given that the bisector itself can be of high degree. And now intersection between two bisectors is going to be of even higher degree curves on that. So we can see that challenging situation now we are left with. So let me just try to address some of them in the first one, and then we'll slowly move on to the next one. So one of the algorithms that we developed quite a long back, what you can see the detail here, which was an SPM paper in 2005. So we came up with some idea on how to process a bisector so that you can end up in the Voronoi diagram. So I'll just go through the details of it a little bit, not in greater detail. As you can see, first step is to come up with a bisector function, and a bisector in general can be represented in this particular form, what is called as an F3 function. This is an implicit bisector function, and the bisector will actually be obtained as a zero set of this function f3. So that is the idea. You basically lift it into the third dimension, doing a surface, and then when you are solving it in a TR plane as a zero set, you will actually get back your bisector. So I'll just probably demonstrate that shortly. Okay, so we'll be using what is called as the IRIT modeling environment. Some of you were familiar with Gershon Elber. He's developed this IRIT modeling environment, which is more like a coding platform, and it is available for free to use for academic purpose. So if you go to this website, you can download all of the IRIT files. The latest version will be available, and there are also instructions on how to compile and run. So what I'll be using to demonstrate some of them is by using IRIT. So let me just switch to IRIT little bit. Just can you people let me know if I are able to see this after I start. So are you able to see this surface that I'm showing?
Yes.
Okay,
It's
great.
good. Yeah.
Thank you. Yeah, so you can see this is the F3 surface that I just talked about in the function between two curves, as you see shortly. And the zero set of this function that you see in the white color will actually be the bisector. So let me just run through that bisector, and maybe I'll give you some idea on the complexity of it. So I hope you are able to see these two curves. Let me just little bit scale it up. Okay. So you see these two curves, C1 and C2, you can think of parametric curves, and you can see the bisector is pretty complex now. It has a very different weird shape, and you have to somehow represent this. That is what that implicit function is about. So let me just show you the complexity as we can see. Suppose if you are taking an angular bisector, we see a one-to-one mapping between one curve to the other curve via the bisector. But here you see that will be a spectacular failure. There won't be any one-to-one mapping. I'll just show you the normal mapping, and it will be in pink color. So are you able to see these normals? As you can see that when we are tracking the normals on the one curve, there is a corresponding normal on the other side, because that is the definition of bisector. It will be equidistant. As this guy goes here, you will see that this bisector will start flipping on this curve C1. You will be observing that. So this starts flipping here, it comes back. Okay, that's why it traces the other portion of the bisector. Even this is also a bisector, as you can see the equidistant points on both curves via the pink normal segments. You can see that the mapping is not anymore one-to-one for a point here. You will see there is one point here on this side and one point on this side, and there is a top point. So this bisector itself is not anymore one-to-one mapping, but then we are supposed to process this bisector to get to the Voronoi. So that is what we are trying to do in this particular algorithm. Let me just go back to the algorithm. So we saw the first step of implicit function, which is the F3 surface, and then how to go to the bisector, which is the zero set of the function. So it's an implicit bisector representation that we have. So as you can see, it was pretty complex. So we had to do some geometric processing on that. You can observe that in this particular case of two ovals having complex shape, and we will observe that in this particular instance, let me just show these cases little later on. It will have four different components, and we will be able to eliminate three of them to retain one, and I'll show you the constraints how we eliminate them. So before that, we just split this bisector function. As you can see that it was a very complex function. So we'll just somehow make it into monotone by using the splitting into monotone pieces. So you will see that the curve can be split into monotone pieces, and we use this John Kaiser algorithms on the splitting of curves. And first step is to split into monotone pieces. As you know that monotone pieces are a little easier to handle. So we are trying to split into monotone pieces. Then we apply what is called as a orientation constraint. As you can observe here in the later slide, I'll show here, it's more detailed. So you can see that there are four segments here. This LR indicates the orientation. Suppose if you are in two curves, and if you are, let us say, you are representing them in a counterclockwise fashion, both of them in a counterclockwise direction, you can see if there is a point here on the bisector, okay, you can see that this point, it will be to the left of this curve, and so it will be to the left of the other curve. So essentially, we see that there is only one component which is to the left of both here, and this is the only one component that we'll require. So this we call that as an LL constraint. And by applying the LL constraint, we are removing the other bisector portions like the LR, RR, and the RL portions. As we know that the Voronoi between two curves C1 and C2 will only need the LL constraint or the left constraint. Basically, is the orientation. We only want the left or the points on the bisector lying to the left of C1 as well as to the left of C2. That is what we basically mean by an orientation constraint. So if mathematically we can represent this orientation constraint, you can see that there are four components here. After we apply that, we will get only the one component that you can see in the bottom picture. So basically this reduces the complexity of the bisector to a great deal. So first step was to basically apply the constraint and you get a minimal portion on the bisector. This is what I discussed now. And then we apply what is called as a curvature constraint. Let me just give a geometric field. This is more complex mathematically. So the idea here is that if you take any point, like a point on a bisector, as you can see here, and you observe what the points at the touching of the curves. So if you observe that the curvature of the ball that you see here has more curvature than the curve at this particular point. So you can see that the curvature of the curve is much higher than much flatter than the curvature of the ball. Ball curvature is much higher than the curvature at this point. For example, if you observe here, okay, you can see the curve is much highly curved than the corresponding ball that you have. So the ball curvature is little flatter and you can observe that the curvature of the curve is much higher. So basically what we are trying to say here is that we are trying to eliminate points that satisfy what is called as a curvature constraint, where you see that the ball curvature is somewhat lesser than the curvature of the curve. So that is what this mathematically it is represented here. And we are applying this constraint, and you can see the next picture, you will see that after applying the constraint, the bisector that was here before, you see that it has removed some of these portions, as you can observe by just the curvature constraint. So the curvature constraint eliminates some portions of the bisector so that we can go to Voronoi diagram after that. So then we apply what is called as a lower envelope procedure, which is a standard one. Since we have monotone functions, if you are given two functions like that, the lower envelope will actually eliminate these portions and will give only this final portion, which is what essentially we need. As you can observe in the previous picture, we have particularly like this. Ultimately, we want a picture like that, which will be the Voronoi diagram on that. So we are basically using what is called as a lower envelope procedure, and we can go from the Voronoi diagram. So these are the details of it, but a little bit skipping on the details. So I'll just show you some results after we apply this entire algorithm, as you can see in this particular step. Yeah, these are the entire steps of the algorithm. So we first given two curves. We first form the bisector implicit function, then you split into monotone pieces. Then you apply the curvature constraint and the orientation constraint. Then apply the lower envelope algorithm. You will actually get the Voronoi cell in this particular case. You don't get the diagram actually. You only get the Voronoi cell for C0 or C1 or C2 and so on. So let me just track you with some results on this. So you can see that there are three curves here, C0, C1, and C2. If you observe the bisector between C1, C0, and C1, you can see even though it is an implicit function, you can see it's a very complex one. From there, you are supposed to go to the Voronoi cell, at least in this case. So you can see that after all the processing, you will be left with only a smaller portion from the bisector. As you can see, it is very complex here. We have eliminated a lot of them, and it is in a much better shape now. And using that, we generate the Voronoi cell by computing the same thing between. Now remember, we are doing Voronoi cell for C0. That means we have to do for C0, C1, and then C0, C2, and so on. Here we have only three curves, so we are kind of little bit, breathing easy. So we got to first generate the bisector for this guy, do all the processing, and find the generator bisector for all the processing. Then you do the lower envelope, and then you will get the Voronoi cell. So you can see the result from that. So doing all that, you will end up in the Voronoi cell for this. So you can see C0. And any point here, as you can observe, will be closer to C0 than to C1 or C2. So that means this is a Voronoi cell of the point C0. And so if you do for C1 and C2, then you can actually generate the full Voronoi diagram composing of Voronoi cells. I'll show you a few more results on the Voronoi, and then I'll run the code to show you. So these are all some more results. We can see that non-convex curves, other curves can also be handled. But these are all represented as a Bezier or a B-spline curves of higher order, sometimes 4, 5, and so on. So we have some results on the non-convexity. I will probably run the code for you to assimilate the idea. So here are the two curves, as we already know that how the Voronoi will be there. So once you run that Voronoi cell, you will see the green color one, and you can observe we have demonstrated the Voronoi cell for the curve C naught, and you will show more results on that. Remember, this is running directly; it is not a video, so it is performing locally, and then it's reasonably fast, but it's still a Voronoi cell. So you can see the middle portion of the curve, and this is the Voronoi cell in green. And any point here in that, you can see that it will be the Voronoi, it's in the Voronoi cell of the curve C naught. Let's say this is C naught and so on. So I'll show you a few more examples. Yeah, this is the one that I show you in the slide, and this is also running pretty fast. So here is the Voronoi cell and few more examples on that. Little bit. So now basically we are generating the Voronoi diagram composing of the sets of Voronoi cells. So we have the set of Voronoi cells forming the Voronoi diagram. Of course, it will be preferable to directly compute the Voronoi diagram without generating the Voronoi cells also. But in sometimes generating Voronoi cells makes possible some of these parallel implementation, which I'll discuss little later in today's talk. So yeah, these are all some examples, as you can see on that. Okay, so this is probably going to come little later. So we can see that some challenges we have gone as outcomes. For example, we instead of performing the intersection between bisectors, so we replaced with a lower envelope, but then that requires the splitting into monotone pieces and so on. So we need to do some geometric processing like monotone pieces. But even after that, we are computing only a Voronoi cell. If you want to compute the Voronoi diagram, we have to do a repeat computation of Voronoi cell. And of course, we had looked at several constraints like the LL constraint, curvature constraint, and so on. So still a lot of geometric processing required, but we have made some improvement. Rather than intersection of bisectors, we used a lower envelope idea. So now what are all the challenges that we can still see or improve upon? As we observed in the previous case, like we had this complex bisector. By some applying constraints, we are able to reduce it to a simpler shape. But then you can observe that this is the only the shape that plays a role in the Voronoi diagram. This is the Voronoi edge, right? So you can see from here, we should go here by so much of processing. So the question that comes to our mind, okay, is it possible to avoid such a complicated bisector itself? Is it possible to not compute the bisector, still compute only the topology of the Voronoi vertices? So can we somehow find only the Voronoi vertices and then compute the local bisector? So this is what we have been trying in the last few years, and we have developed pictorial. I will try to see how it is. So if you are knowing these curves, okay, these green color are the curves, and somehow you can see that if you observe between three curves, there will be what is called as a three-touch disk. If you are familiar with Apollonius diagram and the circle, this is very similar to an Apollonius diagram. We call this as a three-touch disk. So the three-touch disk and the center of any three-touch disk will actually be a Voronoi vertex. So now if you are given, let us say I'm giving three curves, something like that, okay. Somehow can I find the circle that is touching these three, and the Voronoi vertex will be the center of the three touching disk. But you can imagine there will be several curves, and so you can observe that some of these things that if I try a three-touch disk between those three curves, it need not be empty. So that not empty meaning that it is cannot be qualifying for a Voronoi vertex there. Now I can do a simpler process. So I can probably take an NC3 curves and then try all the three-touch disk and find which are all empty and so on. But you can observe that the complexity of such a thing will easily be of n cube, if not more, because you have to test for against all other curves. And in terms of complexity, that will take a big beating. So how do we reduce the number of computations and still keep it little better? For example, can we do it in O of n square? So that was the basic idea. And the idea here is that, let me just go to that. So if you are having three curves, as you can see, CA, CB, and CC, and if you can compute this disk, which is the minimal disk, which is what is called as, we call that as an antipodal disk, and then the three-touch disk, you can only compute the bisector between this disk to the center of this disk. That means I'm going to use only a very small portion of the curve. For example, to compute this bisector that I have, I'll probably use only this portion on one of them and this portion on another one. Unlike I'm going to do an entire one where you can see that the one bisector complexity was very high with so many segments. I'm only going to compute a very small portion of the bisector between these two curves. So this is what the idea that we developed recently, and we call this as a touching disk method. So first, I'll probably give some run through of the algorithm, not in a greater detail, but in a somewhat in a faster fashion on that. So we just compute the antipodal disk, if what are called antipodal disk between two curves, and generate Voronoi only when there is a three-touch disk is empty. And we generate the, as we can see in this picture, we are generating the Voronoi diagram, which is in black, is a very, very local Voronoi diagram. It has very, very small segments for the bisector. It doesn't carry the full bisector segment. So this is the whole hypothesis in which we are developing this entire algorithm. I'll just show you the pipeline, but maybe too complex to explain all the things in detail. So for example, we start with computing all pairs of antipodal disk, which is why the algorithm is O of n square. And then we keep on building what is called as a directed edges between antipodal disks, and then compute the TTD disk as we progress further, and we somehow find when it is empty. Okay, there are a lot of details which I'm skipping here. So if you go to the paper, I think if you go to this underlying paper, you can find more details on that. So by building this sequence of ADs and TTDs, we actually build the topology of the Voronoi diagram, which is basically only the Voronoi vertices and the local portions of the curves. For example, in this particular case, you can observe in this shape that only the Voronoi diagram is computed within a very small curve portion. So this is the Voronoi diagram or the Voronoi edge that we have. So by building these kinds of ADs and TTDs appropriately and finding the emptiness, we show that between two curves, when you want to generate a Voronoi diagram, you actually have to use a very small portion, and then you compute only the local bisector between them. So you already know that if I compute the entire bisector between these two curves, it will be of very high complexity. But we have reduced that complexity to a great deal by using what is called as an antipodal disk and touching disk. Three-touch disk basically is an Apollonius circle problem on that. So by building this, we are able to generate this entire Voronoi diagram. As you can see that in the previous case, we had a Voronoi cell. Now we are able to generate the Voronoi diagram by suitably manipulating what are called as ADs and TTDs. So the entire algorithm, we can go into the details of it in the paper. So we addressed the key challenge. The key challenge was avoiding the global computation of bisectors where it will be very complex bisectors. So we kind of addressed that by somehow finally finding the local computation of the bisectors, as you can see, which is very, very small compared to the entire bisector that you have to start with. So this is the key idea of our algorithm. And so the highlights basically are we eliminates the need for computing a global bisector, and we are using only the local computation. As I mentioned, we are computing the ADs and TTDs. TTDs are the three-touch disks. ADs are the antipodal disks. So three-touch disks are very similar to the Apollonius problem. But as I already mentioned, we are using the IRIT environment for computing the three-touch disk and antipodal disks and so on. And it can handle non-convex curves. And in fact, in this particular paper, we also show that we can compute related structures like the Delaunay triangulation, alpha half, etc. And the somewhat a downslide is the O of n square complexity, but when compared to the computational complexity reduction, I think this is probably not too bad, but we will see that this can be a downslide and we can still improve upon this number. So that is what our next challenge that we are looking at. So how do we reduce the algorithmic complexity? So we already have a O of n square. Can we do better than O of n square? And since we are using exact curves like that, it is still a lot of work. So can we somehow sample curves, right? And then try that. Okay, can we take some sample points and try that? So and then is it possible to develop a parallel algorithm? These are some of the challenges that we are looking at or looked at in the recent past. And then I'll try to address some of them. But before we go that, if you do the sampling of the entire curve, the Voronoi diagram will be very approximate. Then we have to process a lot to actually remove so many segments. Like these segments are all unwanted segments. So the number of unwanted segments can become very high because of this approximation or because of the sampling. So maybe it is not wanted to, we don't want to sample the entire curve to actually go for the Warnock diagram computation. That actually becomes a point set computation. But you can see that it will be a discrete approximate version of the continuous one. So we don't want to probably sample the set of curves as such. Rather, what we try to do is that we use what is called as the Delaunay triangulation. As some of you may know that if this is the Warnock diagram, the dual of the Warnock diagram is the Delaunay triangulation. So we leverage the idea of dt from the samples and to get the topology of the structure, and then we do the three-touch disk computation. I'll just give brief account of that. So we can see that first we are taking the centers of all the, so this is basically not for curves. Actually, we reduce the problem for circles. We are actually not handling, though you want to handle this for generic curves as what the previous algorithms were, but we attempted this in circles to show that we are able to go from a of n square to a lower number. So what we leverage here is the center of the circles. And if you compute the Delaunay triangulation of center of circles, can we get the topology from the dt? That is the question. But if you can observe here, this is the Warnock diagram of the circles. And if you take this Warnock edge, you will observe that the circles C1 and C2 have to be adjacent so that you can compute the Warnock edge between C1 and C2. But if you look at this particular Warnock diagram here, there is no connection between C1 and C2, which implies that there is no Delaunay edge between C1 and C2, and C1 and C2 are not neighbors. So this means that you cannot compute the Warnock diagram between C1 and C2, which is an incorrect conclusion. So if you just use the centers of the circles to get the Delaunay triangulation and try to get the neighborhood, then it is indeed going to be an incorrect answer. So how do we, overcome this challenge? So we propose what is called as a sampling idea. We just uniformly sample all the circles and take the dt. That is one possibility. But we showed that you don't require to take so many samples on every curve. We can do what is called as an adaptive sampling or a dynamic sampling. So we can see that this requires only 3 samples on this curve, and we greatly reduce the samples. And finally, we showed that between these two edges of a dt, you only need one arc to come in. That means we only need a one sample between these two other samples. So we basically use the dt of the circles. Then we compute all these intersections of the dt's with circles, and then recompute the dt with the new points added. And then we use that to get the dt of these new points, which will actually give a correct neighbor, almost correct neighborhood information. We are not exactly saying everything will be captured, but we have proved that this will help in getting the neighborhood for the Warnock diagram, through which we are actually computing the Warnock diagram itself. So again, skipping too many details, this approach, we are able to get the degenerate case where you can see that for one point, which is the Warnock vertex, you'll have several circles around that particular point. Means that this point of Warnock vertex is equidistant to more than 3 circles. So we can handle degenerate cases. And here we have circles that are intersecting, which are also little complex to handle in a numerical way. These are all challenging ones in a numerical way, but we could handle it topologically using the Delaunay triangulation, centers and samples, and so on. So we are able to get for a larger number of circles, and this paper we have published in GMP 2021, and you can look at the paper for further details. So we have improved that further, and we have developed a parallel algorithm for that using the sampling idea. As we discussed in the previous thing on challenges, we can see how we can go to parallel computing, but since we cannot give all the details, I'm just giving a nutshell. So you can see that Warnock cell of C1 and Warnock cell of C2 are kind of disjoint. So that means that we could somehow leverage the idea of parallel computing. So this is what we showed in this particular paper, which was again published in GMP 2022, and you can probably get more details from there. So just moving on to give some idea of the bisectors in 3D, since we are done a lot on bisectors in 2D at this point of time for planar curves, I'll just give a glimpse of what will happen in 3D. You can observe that even in 2D, the bisectors were very complex for general curves. So obviously it is going to be more complex in 3D as well. And these are all some examples I'm citing from the Gershon and Kim's paper. I don't know whether it's very clearly visible that this is actually it's very similar to a case of a point and a circle where you had an ellipse as the answer. So in a similar way, maybe I should change the color. So if you previous case, if you had a point and a circular arc, we know that the bisector was an ellipse. Similarly, if you have a point and then a sphere, you will see that this is actually an ellipsoid. So a kind of a counter one in the 3D case, this is an ellipsoid between a point and a thing, and you can see that between a point and a sphere, when the point is outside, actually this will be a hyperbola of two sheets on that. So you get a similar answer, but somewhat more complicated on the 3D surfaces. So this will become hyper. So you can see that if you want to go to Warner diagram from these bisectors, it is going to be a little bit of a nightmare. So you can see some more shapes between a point and a torus. You can see how the bisector surfaces, and it's add more and more complexity as you keep on increasing, and you go for other primitives like cones and cylinders and so on. You will see that the complexity of the bisectors are ever increasing on that. This is only bisector, and remember, we have to go to Voronoi from bisectors. So these are all some examples on space curves. So if given two space curves, this is the bisector. You can see there is a circle and a line. So these are all two space curves, and you can see the surface, bisector surface, and these are all basically variants of that. So I'll probably show some demo, and that will help in understanding better. And you can see that bisector surface is increasing in complexity. So you'll see that in a general two surfaces case, you have to trace it numerically. We saw a very similar 2D example some time back, and similar example is between a plane and a high curvature surface. You can see how this bisector surface is, and you can observe that it is pretty complex. So this is a surface bisector case, and you can do a numerical idea of it, which was presented by Gershon and Kim long back. I'll just, before I'll move on to this one, how much time I have?
It's supposed to be 55 minutes, but it can be
Okay,
maybe
I'll
longer.
just stop it,
Yeah.
maybe give you some demo, so feel, and then I'll stop it. I think then we can invite more questions.
Okay.
So
Okay.
one demo I'll just give on that to understand the complexity of the bisector. So we see here, so this is between two space curves, in this case, two space lines, and see the bisector is pretty complex as you can observe. So I'm just going to run through this. You can see the animation and see how the bisector is increasing in complexity. You saw these cases in my slide, and yeah, so so these are all some cases. So you'll see the animation between a plane and a point, and that green color is actually like a parabolic surface, and we will animate and see the how this surface is increasing in complexity. It's not anymore a parabolic after that. So these are all some examples that I showed you in the slide, and yeah, you can see between two space curves. So the bisector surface can be pretty complex. And this is bisector surface between two generic surfaces, and I'll just run through that. It can be again quite complex. So the white surface is the bisector between the two other surfaces in red, and I'll just try to move this guy here. Yeah. So these are all computed in real time. Okay, it's not actually a video demonstration. So it can be see that it is getting little slower, but you can observe the complexity of the bisector surface, which is in white color. Yeah, I mean, this is the surface, bisector surface that you can see in white. So I think, yeah, I'll probably just okay, you can basically see that it is getting into a very complex shape, and so I'll just probably leave with the fact that we actually have developed a Voronoi cell algorithm parallelly for a set of spheres, and I'm not probably going to the details of it. Some results that we have, and we published that recently in the last SMA, I think, okay, SMA 2022. Okay. So with that, I think I'll just give some idea on what are the further work that we can do. Like one is to dynamic sampling approach to general curves, and then three touch disk to higher dimensions, like a four touch disk and so on. Sampling approach to spheres, and we can try for Voronoi diagram of our general surfaces. So with that, I'll probably end my talk with acknowledgements, particularly to my advisors. Quite a few of them I had, unfortunate to work with a lot of people both from India and abroad. So Process Gurumurthy, Srinivasan, and then I worked with Gershon and Gil and Myangsu. And my collaborator on the Voronoi was Ido. And of course, thanks to all my students, and in particular the students who worked with me on Voronoi diagrams, Bharat, Vishwanath, Manoj, Arun were my former students, and then Minu and Harita, the current students. And I would like to acknowledge Minu's help for putting up a lot of effort in the slide preparation. So with that, I'll end my talk. I'll leave the floor for questions.
Okay, thank you, Dr. Ramanathan, for the fascinating presentation. Now we have some time for questions. Uh, Audience can type your question in the chat on YouTube or Bilibili, and I will read it for you. I have some question. Uh,
Sure. Yeah.
uh, does the algorithm ensure the topological correctness of the computed Voronoi diagram, especially when dealing with some complex shape set?
Complex shape is quite difficult actually. Probably for the cases like circles, we were able to show correctness in terms of topology. And in terms of spheres, we were able to argue. But in general one, we cannot say exactly that how many Voronoi vertices will have. Maybe I'll try to give some feel for that. For example, if you are taking a simple shape, the Voronoi diagram can actually become little different. So if you take a simple shape like this one, right? Like an
Yeah.
okay, I
Mm.
showed it different color. I think it's bad. So okay, let me try. So if you take a shape like this, then maybe the Voronoi will be something like this. So for a closed one, I'm telling. But if you slightly change the shape, okay, topologic like something like that. Okay, then the Voronoi diagram can become very different. So it may not be the same, and the number of Voronoi vertices may not be really this number can be different. So it's very difficult to assess the topological correctness in general. I mean, we given a shape, I don't think there is any a strong number on how many Voronoi. It's order of n is the overall idea. N is the number of vertices or edges. But there is no certainty in how many Varna edges, how many Varna cells should be there. I think as far as I know, and maybe there is some improvement. We have seen some results like that for simple polygons. Given a simple polygon of n sides, there is some work on how many Varna edges, how many Varna cells have to be there. But what you are asking is for a very complex shape. I don't think there is a definite answer, as far as I know, at least.
Okay, thank you. Uh, for the 3D case, you just share
Yeah,
some results about the spheres, right?
correct.
I just wondering, uh, can can this algorithm be applied to general surfaces
We are
like a
actually
level
trying for
surface?
that. That's a very good question. We are also attempting to do that. But actually, what we did here was to go with a grid-based approach with something what is called as a lower envelope and the intersection from the samples of the spheres. So potentially, yes. See, the one thing is that since we are using the lower envelope and the bisectors are known between two spheres to be hyperbola. So we can leverage some hyperbolic equation to do this. But in general, if you take two surfaces, it is non-rational. I mean, it has to be numerically done. So that actually increases the complexity to a great deal. We have done a tracing method long back to generate the Varna edges. But still, I think it is numerically a lot more to be done. And a procedure like what we did to extend it to there, I don't think it is a direct extension is immediately possible, but modifications is what we are trying. It's a very complex question.
Yeah, thank you. Uh, My last question is, as we know, your recent research interests include deep learning.
Yes.
Is it possible to apply deep learning methods to the Voronoi computation?
Very interesting
Do
question. Excellent question and very interesting. Actually, we are trying that way as well. And we have tried, see, deep learning, geometrically, it can become very difficult. But if you consider this as an image and do that as an image problem, right? If you try, like, make this shape that you're having into an image and then do a data of these middle axis or the Voronoi as images, then yes, there is some possibility that we have found it can be done. But I don't think that may be possible if you consider this as a geometric object. And deep learning there, I think, could be extremely difficult to model the network. And we actually are trying with images, which seems to be showing some success. So we want to see how we can convert into a maybe a combination of algorithmic one plus the deep learning will help. I don't think entire 100% deep learning is possible. I mean, that is my perspective on this.
Okay, okay, thank you. Uh, if no more question from the audience, let's thank Dr. Ramanathan again.
Thank you.
Thank you.
So I'll stop sharing the screen now.
Yes.
Something happened. Let me just. Inside that. Moses. Okay.
Okay,
Yeah,
thank
I
you.
think I'm done.
Yeah.
Thanks for
So
inviting me again. Yeah.
so let's move on to the next talk. Uh, our next speaker is Dr. Yinyang Xiao. Dr. Yinyang Xiao is the assistant professor in the School of Mathematics and Computer Science. He received his PhD from Xiamen University in 2020, and he has published several papers on Voronoi and power diagram computation and their applications. So let's welcome Dr. Yinyang Xiao to begin his talk.
Thank you, Professor. Uh,
So you can share your screen.
can you see my screen?
Yeah, perfect.
Oh, okay. Good evening. My name is Yinyang Xiao. I'm from Nanchang University, China. I appreciate to have this opportunity to present our recent work. The title of my presentation is Meshless Power Diagrams, which is about the fast computation of power diagrams based on k-nearest neighbors. I will introduce this work in 7 sections. Firstly, let's take a look at the background. Voronoi diagram is a classic structure for region partition. Given the set of Cs, they can define a partition of the space. Each seed dominates a subregion of the space, which is also called Voronoi cell. For example, a seed Vi corresponds to a Voronoi cell omega I. It can be defined by this equation, which means the cell omega I contains the points whose distance to the corresponding seed is no greater than that to the other seeds. An ordinary Voronoi diagram divides the whole space, so some Voronoi cells are unbounded, containing infinite points of the space. In practice, many applications are interested in the intersecting part between a given domain and the Voronoi cells, so which is called a clipped or restricted Voronoi diagram. Here shows some examples of clipped or restricted Voronoi diagrams. The computation of Voronoi diagrams has been extensively studied, and many methods have been proposed, but some of them were developed for the planar domains and are hard to use in high dimensional spaces. For constructing Voronoi diagrams of general cases, the duality of Delaunay triangulation and the measureless method are popular. This page shows the Delaunay triangulation-based method. It has to construct a Delaunay triangulation of the given seeds. So each seed can explicitly obtain its connectivity from the triangulation, and the corresponding Voronoi cell is then obtained by clipping the given domain using the bisectors of the seed and its incident neighbors. So this method highly relies on the Delaunay triangulation. But the construction of Delaunay triangulation is time-consuming if the number of seeds is large. So another kind of method, which does not need to construct triangulations, attracts much attention in recent years. The method is called KNN-based method or the measureless method. An observation is that each Voronoi cell is the intersection of half spaces between the corresponding seed and all the other seeds. So each Voronoi cell can be obtained by clipping the given domain using the bisectors of the corresponding seed and all the other seeds. However, it is not necessary to visit all the other seeds in such cell generation because each Voronoi cell only involves some nearest seeds. Let's take a look at this example. To compute the Voronoi cell of xi, this method finds some nearest neighbors of xi in ascending order according to their distances to xi, and then uses the bisectors of xi and its neighbors to clip the given domain. The clipping procedure can be terminated in advance once the distance from xi to a bisector is greater than the maximum distance from xi to its cell. In the right figure, when we visit x8, the termination condition is met, and we can output the cell of xi. Now, let's focus on the power diagram. Power diagram is one of the generalized Voronoi diagrams, which is defined by a set of weighted seeds and the power distance function. The power cell of seed Vi can be defined by this equation, and the figure is an example. Because each seed is attached a real number called weight, the additional degree of freedom makes the power diagram more complicated than the Voronoi diagram. So only few methods are available to compute power diagrams of general cases. Orenheimer found that each weighted seed can be mapped to a hyperplane in the higher dimensional space. The intersection of the half spaces above these hyperplanes is a polyhedron. Its faces projected back to the original space are the power cells of the given weighted seeds. So he introduced an algorithm to construct a convex hull in a higher dimensional space to produce power diagram results. But this method is too complex to use in practice. A more common approach is based on the duality between the power diagram and the regular triangulation, which is similar to the duality between the Voronoi diagram and the Delaunay triangulation. Although there have been robust and high-quality implementations of this method, the problem is still the high cost in constructing regular triangulation of the given weighted seeds. So we are interested in the computation of power diagrams without the construction of triangulations. We wonder that can the measureless method be applied? Several works have attempted to directly extend the measureless method to compute power diagrams. However, their extensions have a strong precondition that the weights of adjacent seeds have close values, which evidently cannot be used for general cases. Fortunately, we found that any power diagram is actually equivalent to a restricted Werner diagram in the space of one dimension higher. This property allows us to apply the meshless method to the computation of arbitrary power diagrams. Let us see more details. As just mentioned, the power cell is defined by this equation. We can see that the power distance function is not additive in the weight dimension, resulting in the neighboring relationship between weighted seeds is uncertain. For example, the green cell of seed Vi may be determined by its nearest 4 seeds. However, if there is another seed whose weight is large enough, it will affect the cell of Vi, even the seed and the Vi are far away from each other. This obstacle makes the meshless method cannot be applied directly to the computation of power diagrams of general cases. Because if we want a correct result, we have to visit all the other seeds to construct each power cell. Or if the meshless method is directly applied to the computation of arbitrary power diagrams, it cannot guarantee the correctness. So it is actually an approximate result. Our solution is simple. We introduce a parameter eta, which is greater than the maximum weight, and we add it into the distance function. The new partition controlled by the new distance function is actually the same with the original power diagram, because the inequality relation does not change after we add 8. Now let's do some further transformation. Because 8 is larger than the maximum weight, so 8 minus Wi or Wj must be greater than 0, and we can treat the equation like the following red part. Let's denote y and p like this. They are actually the points in D plus 1 dimensional space. We refer to p as the lifting point. So the definition of power cell can be finally rewritten as the button omega I. Now it is very clear the distance is actually the squared Euclidean distance, which means omega I is the Werner cell of the lifting point pi. Please note, because the domain is restricted in the RD space, so the power cell omega I can be viewed as the restricted Werner cell of pi. The equivalence can be illustrated by this 2D example. The green power cell of Vi equals to the restricted Werner cell of the lifting point pi. This property allows us to apply Werner generation methods to the computation of arbitrary power diagrams. It is worth pointing out that we have 2 options for lifting each weighted seed, which are P and Q here. One is above the RD space, and the other is under the space. The restricted Werner cell of Pi is exactly the same as that of Qi. We can use this property to accelerate the computation of meshless power diagrams. I will talk about it later. Now we can introduce the meshless algorithm for computing power diagrams. The input includes a bounded domain M and a set of weighted Cs. The domain may be assembled by a set of region elements, like 2D, like the polygons in the 2D and the surface cases, polytopes in the 3D case. We first lift the weighted Cs to a set of points in the higher dimensional space, and then construct a KD tree for the subsequent k nearest neighbors queries. Each power cell omega I is initialized as the domain M, then is sequentially clipped by the bisectors of the corresponding lifting point Pi and its k nearest neighbors. The clipping procedure will not stop until the termination condition meets. That is the maximum distance from Pi to omega I is smaller than the half distance from Pi to one of its neighbors. Here is an illustration. After initialization of omega I, we find some nearest neighbors of Pi among all the lifting points and iteratively construct bisectors to clip omega I until the termination condition meets. Here shows the first clipping. The bisector between Pi and Pj1 is constructed, and because the termination condition is not met, omega I is then clipped by this bisector. The result is shown as green in the right figure. The next bisector is between Pi and Pj2. Because the termination condition is still not met, omega I should be clipped by this bisector. The green part in the right figure is the result after this clipping. We can see that omega I becomes smaller and smaller, so the maximum distance from Pi to omega I will get smaller after visiting more neighbors. On the other hand, the distance from Pi to its neighbors will be larger and larger. So after some times of clippings, the termination condition will be finally reached. So the power cell is generated. See the green cell in the right figure. That is the power cell of CWI. Once all cells are generated, the power diagram is obtained. If the domain consists of a set of small regions, it is not necessary to compute the intersections between a power cell and all the domain regions, because a power cell can only cover a few number of regions. So in this case, the propagation strategy can be applied. Let's look at this figure. Suppose that we already know that region F0 and cell omega 0 are intersected. So we can use the meshless clippings to obtain their intersection. That is the orange polygon in the right figure. The result of the intersection can provide more pairs of region and cell that are intersected. Specifically, we can visit all the edges of the orange polygon. If an edge comes from the original polygon of F0, for example, Q1 to Q2, we know that the cell omega 0 must intersect with the neighboring region of F0. That is F1 here. Well, if an edge is generated by a clipping, for example, Q4 to Q5, we know that the neighboring cell of omega 0 must intersect with the current region F0. So some more pairs can be found after we visit all the edges, and these pairs can be further processed by using the meshless clippings. Now, let's focus on the accuracy of our result. In some implementations of meshless Voronoi diagrams, they use neighbors list with fixed size. So the termination condition of clippings is not guaranteed to meet, which will result in that part of the Voronoi cells may have larger volume than the accurate Voronoi cells. So their result is approximate. While in our implementation, if the termination condition is of clippings is not met, we choose to find more neighbors to continue the clipping. And because the domain is bounded, the termination condition will finally be met. And our method produces accurate power diagrams, not approximate. Next, we should talk about the choice of parameter 8. We know that 8 controls the height of lifting points to the RD space. A lower 8 will make the termination condition of clippings easier to meet. Here is a comparison experiment. We set different 8 values to test the efficiency of our method in the 2D surface and 3D cases, respectively. And we plot the average clipping numbers and the commutation time. The 3 figures in the bottom line show a similar change, that the result indicates that the lower 8 leads to fewer clippings, thereby saving computation time. So we suggest a lowest 8 value. That is actually the maximum of the input weights. Next, let's see how to speed up the algorithm. As just mentioned, the cell of Pi is the same as that of Qi, so we can accelerate the computation if we replace Pi with Qi in the proposed algorithm. Take a look at this example. Lifting points Pi, Pj, and Pk are above the RD space, and the twin point Qi of Pi is under the RD space. And we suppose that the distance between Pi and Pj is smaller than the distance between Pi and Pk, while the distance between Qi and Pj is larger than the distance between Qi and Pk. So if we compute the cell of Pi, the brown bisector of points Pi Pj is first used. Then the purple bisector of points Pi Pk is used. We can see that by this order, the first clipping is meaningless because the second clipping cuts off the result of the first clipping. In contrast, if we compute the cell of Qi, the blue bisector of points Qi Pk will be first used. And when we use the yellow bisector of points Qi Pj, the maximum distance from Qi to omega I could be smaller than the distance from Qi to the yellow bisector. So we can finish the computation earlier. Based on this observation, we can speed up the computation by replacing Pi with Qi. For the implementation of the acceleration, we still build a KD tree of a set of lifting points Pi. But when we compute the cell omega I, we find the k nearest neighbors of Qi and constructed bisectors of Qi and its neighbors for the clippings. As a result, this trick can speed up the meshless computation because the termination condition can be met earlier, and many clippings that have no contribution to the result can be avoided. The conclusion is demonstrated by this experiment. We compare the clipping numbers and the computation time before and after using the acceleration on different domains. All the three figures show that the clipping number and the time cost are both reduced after we use the acceleration. So that the efficiency of our method is promoted in all cases. Next, we come to the path of results. We test our method on different domains, including 2D polygons, surface meshes, and 3D polytopes. Here are the power diagram results of 2D, surface, and 3D cases, respectively. For each domain, the seed locations are obtained by uniform sampling, and the weights are randomly generated. The seeds are shown as the red and blue discs or balls. Red color means the seed has positive weight, and the blue color means the negative weight. The radius of discs and the balls indicate the absolute value of the weights. This is another group of results. The seed locations and the weights are both randomly generated. Some weighted seeds that have empty power cells are still shown in three figures. Now let's focus on the efficiency. For meshless Voronoi, the efficiency is highly affected by the distribution of seeds. If the seeds are distributed uniformly, like the seeds of the central Voronoi tessellations, the termination condition of the meshless clippings can be met earlier. But if the seeds are generated in a random way, the condition will be met harder. So it has to spend more time to finish the commutation. So the efficiency of our method depends on the distribution of the lifting points, which is actually influenced by the distribution of seed locations and weights. Generally, if the seed locations are uniform and their weights are similar, the lifting points will be uniform. So our method has a higher efficiency. Here are the tests for typical configurations in the 2D case that are random locations with zero weights, random locations with random weights, uniform locations with zero weights, and uniform locations with random weights. We can see that the computation time is the lowest when we have uniform locations with zero weights. The surface and the 3D cases show a similar conclusion. Here, we compare our method with the regular triangulation-based method. We first generate 100 sets of seeds by using the central Voronoi tessellation method, and each of the sets is then attached random weights in 100 different ranges. And we plot their computation time in this figure. We can see that the computation time of our method drops with the improvement of the seed uniformity, while the regular triangulation-based method remains stable, especially in the 3D case. However, our method has better performance for all the tests in the 2D and the surface cases. While in the 3D case, our method is more efficient only when the locations and the weights of the seeds become uniform. Because the cell generation of the meshless method is independent of each other, we also implemented the parallel version of our method. For the regular triangulation-based method, its clipping stage can be paralleled too. So we also compare the parallel version of our method and the regular triangulation-based method in this figure, from which we can see that the parallel version of our method is more efficient than that of the regular triangulation-based method for all the cases. This table is the comparison of the main steps between the regular triangulation-based method and ours. Our method causes most of the time in the clipping stage, while the regular triangulation-based method spends less on clipping because the triangulation provides an explicit neighborhood for each seed. Its most time cost is on the construction of triangulations. Finally, we compare the computation time of regular triangulation-based method, our method, and their parallel versions against the number of seeds. The first row shows the test results when the seeds are randomly generated on different domains, and the second row shows other results when the seed locations are uniform. The conclusion is similar. Our method is faster than the regular triangulation-based method for most cases, but the upper right figure shows the serial version of our method is not good enough. That is the 3D case when the seed locations are random. Fortunately, the parallel version of our method has the best performance for all the cases. Our method and its parallel implementation can provide much higher efficiency than the state-of-the-art method. So it is suitable for applications requiring the frequent computation of power diagrams. In the application of blue noise sampling, Xin presented a variational method, which is called central power diagrams with capacity constraints. High-quality blue noise sampling results can be obtained by minimizing this energy function. The figures show the results after 100 iterations. If we use our method to compute power diagrams in their method, we can save about 8 seconds in the 2D case and 50 seconds in the 3D case. Adaptive remeshing generates a new mesh from a given mesh. And Yan presented a method based on the farthest point optimization over power diagrams to generate high-quality meshes. In their method, if we use our method to update power cells of samples, the experiment shows that we can save about 1 second for each iteration. This is the generation of Voronoi tree map, a tool for visualizing hierarchical data. The test data has 53,000 weighted nodes. By replacing the computation of power diagrams in Nokash and Brandeis method with our method, we can save about 9 seconds in total to generate such a result. Before the conclusion, I would like to present our GPU algorithm for the computation of power diagrams. There are some implementations of the meshless method on the GPU side for computing Voronoi diagrams. They use a neighbors list with fixed size. We know that the Voronoi cells have a different number of neighbors. So for each cell generation, the termination condition of clippings is not guaranteed to meet, and a part of Voronoi cells could have a larger volume than the accurate results. We aim to construct accurate power diagrams on the GPU side. To overcome the accuracy issue, we have to change the way for generating cells. Here, we set up a group of grids and put all the lifting points into these grids according to the coordinates of the points. In the next step, we clip the cell directly by using the grids. Let's see the example. Suppose that we try to construct the cell of the red point, and it is initialized as the domain, which is the green triangle. We locate the grid that the red point is in. we call it the central grid, which is the orange one in the right figure. Then we visit all the points except the red one in this grid and construct the bisectors of the red point and other points in this grid to clip the cell. The result is shown in the right figure. We call the clippings are in the ring 0. Next, we have to find all the neighbor grids of the central one that are the orange grids in the right figure. And still, we construct bisectors of the red points and all the points in these grids to iteratively clip the cell. The result is shown in the right figure. The clippings are in the ring 1 of the central grid. Similarly, we continue to locate the grids in the ring 2 range of the central grid and visit points to construct bisectors and clip the cell. After these clippings, the cell is getting smaller and smaller, or the maximum distance from the red point to its cell is getting smaller. In contrast, the minimum distance from the red point to the grids in the range becomes larger and larger. So the termination condition of each cell generation is that the maximum distance from the red point to its cell, see the blue circle in this figure, is smaller than the minimum distance from the red point to the grids in the ring range. That is the purple dotted segment here. Because the points in the further grids will not affect the cell anymore. This figure is an illustration of the termination condition. It is worth pointing out that the resolution of grids impacts the efficiency of cell generation. If the grid size is large, there will be many points in one grid, so that we have to launch many extra clippings during the cell generation, costing more time to generate result. So a small grid size is good for our method. In this figure, we test our method on different grid size and plot the time costs. We can see that our method with a smaller grid size costs less time. However, if the grid size is too small, we will need many more grids, which is a burden for the GPU memory. We provide a comparison of efficiency with other methods. The time curves of different methods are plotted in this figure. We can see that Liu's meshless implementation is better than ours. The reason is that our method aims to generate accurate power cells, so it involves more clippings than Liu's method, thereby costing more time. Here shows the accuracy comparison with Liu's method. Our method generates accurate power diagrams, while the result of Liu's method is approximate. A part of cells have larger volume than the real power cells. Okay, in summary, we provide a variant for lifting the weighted Cs to a set of points in a higher dimensional space. Then the power cells can be directly obtained by computing the intersections of the Voronoi cells of these lifting points and the original space. Based on this property, we extend the meshless method to the computation of arbitrary power diagrams. The performance is better than the standard triangulation-based method in most cases. We also developed a new GPU algorithm to construct accurate power diagrams. But this method has a drawback that its efficiency is highly affected by the distribution of the given Cs. if a seed dominates a point that is far away from the seed, for example, the red seed and the region corner in this figure. When we compute the cell of this seed, the termination condition of the cell generation cannot be reached even we visit many extra neighbors, resulting in much more time costs. We are developing a new algorithm which is promising to solve this problem. That is all of my presentation. Thank you.
Okay. Thank you, Yang, for the insightful presentation. So we have some time for questions. Okay. Let me start with some questions. In your slides, you mentioned the acceleration strategies for the CPU algorithm. I just wondering, can it be used in the GPU algorithm?
Thank you for the question. Let me go back to the page. Yes, actually, the acceleration trick has already been used in the GPU algorithm, but I skipped the details when I introduced the cell generation here. The real cell generation has a slight difference. In our implementation, the grids are set up for the lifting points above the 3D space. So when a twin point under the space is given, we have no central grid anymore for this twin point. And the cell generation starts from the grids in the ring W, where W equals to the grid height from the twin point to the 3D space. Yes.
Okay. Thank you. For the accuracy issue of the meshless method, if the size of neighbors is large enough, like 200, the cell result should be accurate. So, does your GPU algorithm have any advantages over such configuration of the meshless method?
Thank you for the question. You are right. For existing implementations of the meshless method, when the size of neighbors list is large enough, the cells can be accurate, but it still cannot guarantee the correctness for arbitrary inputs. On the other hand, when the size is large, the time cost and the memory usage for finding the neighbors list will both increase. So the efficiency of their implementations will become lower. So in such configuration, I think the advantage of our GPU algorithm is still the correctness for arbitrary inputs. We even could have better performance on the efficiency because we do not need to spend time for getting the neighbors list. Thank you.
Okay. Thanks. Due to the time limit and no more questions from the audience, let's thank our speaker, Dr. Yinyang Xiao and Dr. Ramanathan Mudugadapada once again. And thank you all for joining. And we look forward to seeing you at our next AsiaGraphics webinar.
Yeah.
Thank you.
Thank you. Yeah, thanks.
Okay.
Yeah.
Thank you.
Thank you.
Bye.
Bye-bye.